This is a video about relative motion. Thanks for the PowerPoint, Dr. Bertrand. When observers are moving at constant velocity relative to each other, we have a case of what we call relative motion. The moving observers can agree about some things, but not about everything regarding an object they're both observing. So let's look at such a case. Consider two observers, observer A and observer B, and particle P. Suppose observer B is moving relative to observer A. Okay? Also suppose particle P is also moving relative to observer A, but at twice the velocity. In this case, it looks to A, from A's point of view, that P is moving to the right at twice the speed that B is moving in the same direction. But let's look at it from B's point of view. From B's point of view, it looks like P, the particle P, is moving to the right at the same velocity that A is moving in the opposite direction. And on top of that, from B's point of view, it looks like object P is only moving half as fast as what A thinks object P is moving at. So as we can see, the velocity measured by two observers depends upon the observer's velocity relative to each other. So let's look at what observer B is seeing. Observer B, if we focus on this equation, observer B sees the particle only going this fast. One way of looking at that is by taking the velocity that observer A is seeing, which is this entire velocity, VA, that velocity, and subtracting the relative velocity between A and B. If we do that, we end up with what observer B sees. What observer A sees is the particle moving at the velocity that observer B notices. So observer B notices that it's going that fast, plus the relative velocity between observer A and observer B, which is that amount. So if we add if we take what B observes and we add the relative velocity, we end up with what observer A observes, which is this entire velocity there. So now for the same problem, let's show that although the velocity observers are different, the acceleration they measure for a third particle is the same, provided that the relative velocity is constant. So let's begin with that equation. Now, as we know, if we take the derivative of both sides, we can find that we get the derivative of v with respect to t, the derivative of v sub a with respect to t, and the derivative of the relative velocity with respect to t. Now, in this case, we know the derivative of the velocity is the acceleration, so the derivative of VB is AB, the derivative of VA is the acceleration of A, and the derivative of this constant, we'll just for the time being call that the derivative of the relative velocity. But as we know, that relative velocity is a constant, so that goes away. And we find that the accelerations that we observe are the same. So this goes to prove Galileo's law of transformation of velocities. If observers are moving but not accelerating relative to each other, they agree on a third object's acceleration but not its velocity. Now that brings up the topic of inertial reference frames. An inertial reference frame is one in which, or where we call them frames of reference, which may move relative to each other, but in which observers find the same value for the acceleration of a third moving particle. So in other words, two different objects will always observe a third object as having the same acceleration. Inertial reference frames are moving at constant velocity relative to each other. It's impossible to identify which one is actually at rest. Newton's laws hold only to be true in inertial reference frames and do not hold true in reference frames which are accelerating. All right, so let's look at a sample problem. In this sample problem, it says, how long does it take an automobile traveling in the left lane at 60 kilometers per hour to pull alongside a car traveling in the right lane at 40 kilometers per hour if the car's front bumpers are initially 100 meters apart? Okay, so let's look first of all to convert from kilometers per hour to meters per second. So 60 kilometers per hour is 16.7 meters per second. 40 kilometers per hour is 11.1 meters per second. So as we draw the motion maps, we notice that we have to draw them as being constant velocities for each. And they're going to get to this location. So if that's true, then we know that this entire distance from here to here will define as x1, and this distance from there to there will define as x2. So we can set x1, this total distance, equal to 100, this distance plus that distance. We know that in general, the distance, as long as the velocity is constant, is equal to the velocity times the time. So x1 will be the velocity of the green car times the time that it's traveling. And x2 will be the velocity of the yellow car times the time that it's traveling. And those two times will be the same. We have to include this 100 meters so that we can actually say that this x1 is equivalent to this entire distance here, x2 plus 100. So in this equation here, we've got one equation with one unknown. So we can solve that as being 18 seconds. All right. Now let's look at another sample problem. It says a pilot of an airplane notes that the compass indicates a heading due west. The airplane speed relative to the air is 150 kilometers per hour. If there is a wind of 30 kilometers per hour towards the north, find the velocity of the airplane relative to the ground. Okay, so we're going due west, 150 kilometers per hour, but we're experiencing wind that is 30 kilometers per hour. Okay, we want to find the velocity of the airplane relative to the ground. So we've got to employ our vectors here. We've got to add them up. So it will be the hypotenuse of that right triangle there. To find the speed, as we know, we would have to use a Pythagorean theorem. So go ahead and solve that to find the speed. And to find this angle theta here, that would be equivalent to taking that inverse tangent. All right, and that's it for this video.